Assessment graph algorithms. For question 1, my answer was true. Dijkstra's algorithm would not work when the negative edge weights are hidden paths. However, if the negative edges weights are outgoing edges from the start node, that means that during the first iteration, it would immediately be considered. Therefore, Dijkstra's algorithm would still work. For question 2, part 1, there can only exist a single shortest path from U to V. Well, here I drew a counterexample where there are two shortest paths from U to V. The first one highlighted in blue from U to B and B to V, and the second one highlighted in yellow from U to C and C to V, both having the total edge weight of 7. For question 2, part 2, a shortest path from U to V must include one or more edges in the shortest path tree from S. As you can see in this counterexample, I drew the shortest path tree from the source, or which is S, highlighted in red, and I drew the shortest path from U to V, which is highlighted in green. You can see here that the shortest path from U to V does not include one or more edges from the shortest path tree from the source. For question 3, if the shortest path tree reaches U and V, then U and V are connected. My answer was true. Here, I can give an analogy. Let's say U is Safeway and V is Walmart, and the source is my house. If there's a path from my house to Safeway, and there's a path from my house to Walmart, is Safeway and Walmart connected, or is there a path from Safeway to Walmart? Well, yes, I can get from Safeway to Walmart from going to my house and then to Walmart, basically saying that U and V are connected because there's a path from U to V. For question 2, part 4, the distance of a shortest path from U to V cannot be greater than this 2.getU plus this 2.getV. This 2.getU plus this 2.getV basically represents this graph I drew before. I mean this analogy I drew before, or yeah, basically saying that there's a path getting from U to V. So if the question is asking if there's a short path from U to V, can this be like greater than this path? Well, if this is, let's say it is greater. If this is greater, then this would not be the shortest path by definition. Instead, this would be the shortest path. Therefore, my answer is true. The distance of a shortest path from U to V, right here, cannot be greater than this path right here. Question 3. This is how I found out the runtime bound for this code. Here we are given the priority queue methods and their runtimes. I want to determine the size of the priority queue first so I can know what n is. Here we know that we're going to add to the priority queue the number of vertices because we're going to visit all the vertices in the graph. Therefore, the priority queue size would be the number of vertices. So everything n here would be replaced with v. Next, I want to determine each of the methods of the priority queue in this code. Here we can see the isEmpty is a constant runtime. Remove min will be v, a number of vertices. Here this is all constant as well, so these aren't really important. This is also the dot contains is also a constant runtime, so we don't really have to care. The change priority as well is a constant runtime, and the dot add method is v times. Then I want to figure out how many times I'm going to execute the statement. Well, for this statement, the remove min, well, how many times am I gonna how many vertices am I gonna check basically? So I'm gonna check all the vertices, right? So I'm gonna run it v times. So this will run v times, and we have v times v, which is v squared. Next, I want to know how many times everything in here will run. Well, you can see here, the statement is basically saying we're gonna visit all the vertices, right? And then we're going to visit the outgoing edges from the vertices. If we visit all the vertices and all its outgoing edges, that's basically saying we're visiting all the edges. Therefore, everything in here will run e times. So all these constant times will run e times. And then this will also run e times, this if statement check. But you should pay attention to the else case, because with the else case is parameter.add, which is the priority queue, right? We're not going to add the priority queue e times. That doesn't make sense, because we're just going to add v times, which is the number of vertices. So this will run actually v times. So this statement here will actually run v times, and v times v is v squared. If we take this overall into account, it'll be v squared. There's two v squares here and here, which is 2v squared. And then if we add the constant here, which is e, I get 2v squared plus e. but the 2 doesn't really matter, so it's v squared plus e, and that's how I got my answer. Lastly, for question 4, my answer was false. Here I drew a counterexample with 5 nodes where I did the topological order of this this graph right here, and I got 1, u, 2, 3, v. As you can see, in the topological order, u comes before v. However, if you see in the graph here, u is not connected to v. Because this is a directed graph, u cannot go back to u1, so u cannot go to 1. Therefore, u and v are actually not connected, meaning that there is no path from u to v.